Today we are playing at home because Marco has been one of our team since a very long time when he started his medical career. He got a degree in medical in MD degree in 18. Then he had a clinical fellowship in digestive disease from 19 to 23, and now is located as postdoctoral fellow at Yale University of Medicine, New Haven, United States. Marco has a track record of in the use of the WISE AI in medicine, and in particular in liver disease. And today we're going to talk about his expertise and his insights in this fascinating field. Mauro, the podium is yours.
Okay, let me first share my screen. Okay. Slideshow. Okay, can anybody see my screen, first of all?
Yes.
Okay, perfect.
You better maximize because it's just part of it. You better maximize.
Okay, let me try.
Yeah,
Now?
perfect.
Okay, perfect. So first of all, let me thank you, Professor Filibelli, for his kind introduction. And as he said, I'm a medical doctor. I'm a specialist in digestive disease, and I work at the intersection between artificial intelligence and digestive disease, so gastroenterology and hepatology. The aim of today's talk is to give you some insights on what generative artificial intelligence is and its possible application in healthcare and specifically in hepatology. So let's start with some definitions. So why is it called generative artificial intelligence? Generative because it's a particular kind of artificial intelligence which has the aim and the structure to create new content. And this new content can be audio, code, images, text, or even videos. And artificial intelligence, of course, because you are talking about systems that are capable of performing a series of tasks that typically would require human intelligence. Why are we talking a lot about generative artificial intelligence? What happened in the past few years? So on November 2022, ChatGPT was released to the public, and this brought something related to artificial intelligence application from something which was deemed as complex and unreachable to something that is accessible to everyone and everyone is using. And the impact was so important and huge that ChatGPT was one of the applications that reached 100 million users in just 2 months. And if you compare the numbers of users that ChatGPT reached compared like to other applications like Telegram, Spotify, or Instagram, you can see like, for example, Instagram took 30 months to reach the 1 million users. So you can see how much interest and how many people were using this application in just a few months from its release. But what is ChatGPT? ChatGPT is called a large language model. Large because these massive neural network powerhouse that has millions or billions of parameters, and these are trained on enormous amount of text. Language because their main task is to process, understand, and generate human language. And model because, of course, you're talking about systems that try to capture linguistic patterns, and with these patterns they try to predict and produce relevant output. Of course, we've been dealing from language models for a long time, and I think that everyone of us is familiar with autocomplete language models that we have on our email, on our application that we use for writing even medical papers, research papers. So I want to just start from the basics and then let you understand the difference with large language models. The more rudimentary language models were statistical tools. So let's say I'm writing an email and I have the autocomplete that is trying to predict what the next word would be after I say like Boston weather is. What happens is that among all the words that exist in our language, the statistical model would pick the one which has the higher probability of succeeding the few words like whether is, and then the autocomplete add this word to what I'm writing. The big problem of this rudimentary language model is that they don't work well, or they cannot handle long range dependencies, which means that if you have a very long test, they can only predict the next word by using just one or two words. And for example, if I'm trying to predict the word rainy, I wouldn't even consider the word Boston, but just weather is. So if, of course, I'm talking about a city in Florida, the most probable word would be maybe sunny or hot or warm instead of rainy. And this language model cannot take this kind of information into account. So let's do a step forward and let's think about these rudimentary language models. And we have a long text coming from a radiology report, and we are trying to produce a task. This task is, for example, to make a summary of this radiology report. And you will think it's impossible to do such a thing with just accounting for the last word of a very long context. So you cannot write a report using only the word these findings, which are the last two words, for example, that are in this report. And large language models were created with the idea that rudimentary language models don't have enough what we call attention to deal with longer context. So we need something that does not only take into account the last, let's say, couple of words, but take into account also all the context that was before. And this is the huge revolution that led to the development of large language model, and that was published in 2017. And the paper, which was cited almost 200,000 times by the main developer at OpenAI, which is the company that developed ChatGPT, was called Attention is All You Need. And they deployed the so-called transformer architecture. The transformer architecture is just a powerhouse of neural networks that are working together one after the other, and it consists of mainly two sections: the encoder and the decoder. We'll be talking about this a little bit more in details in a few minutes. So let's say I need to use this architecture to do a medical task. So I want to determine, for example, which would be the most suitable treatment for a chronic HCV infection in a patient who is a 23-year-old patient who has not been treated before for HCV, genotype 1A, no liver cirrhosis, no co-infection with other with hepatitis A, B, or HIV, and who is currently not taking any medication. What happens in the transformer is that the text is encoded into what we call embedding. So it just converted into vectors, and these vectors are a representation of our language. The most important thing is this is not just a word to number conversion, but this takes into consideration the meaning and the relationship between words. So if I'm talking, for example, about the bank, where I go and get money, it would be like a different vector if we compare to the bank of the river. Okay. Then there is a series of neural networks that try to predict the outcome, and this is called the decoding part. So they generate a series of vectors which should follow or should answer to the question that we're asking, and then the decoder convert the vectors into text. So it's a series of conversion of text into vectors. The vectors are used to predict new vectors, and the vectors predicted vectors are then converted into new text. What happens is that this company that developed large language models took all the data from the internet and did an initial training. Then the tasks were optimized with human supervision. So they had a human grade billions and billions of answers, and then they used these answers to do what we call reinforcement learning. and try to optimize the way these models responded according to human feedback, and they were aligned to what we human want. Just to give you an example of how this large language model may work, let's say I'm a patient. I went to the doctor just to check for gallstones, and they did an ultrasound, and they found an hemangioma of 5.1 millimeters. And I don't know what an hemangioma is, and I asked to a large language model, what is a hemangioma, and should I be worried about this? So, foundational large language model has ingested all the knowledge that is in the internet. So they're able to give rudimentary or even like very good answers, telling us, okay, what is an hemangioma? It's non-cancerous, it's small, and when would follow-up be needed, and just may tell us not to worry about this finding because of a series of reasons. So there is some reasoning on why they're suggesting us something, and the the thing is that these models are not able to incorporate only text, so the question that we're asking, but are becoming multimodal, which means that they're able to process not only text, but images, audios, and videos. So let's say I ask the question in a different way. So I say, I went to the doctor this morning, and this is the image that they took from my liver. Can you take a look of this image and tell me what it could be? So the large language models are now able to like give a rough estimate of what we're seeing in the image. For example, they say it's an hyperechoic lesion of the liver. They're able to understand that the measurement put in the wrote in the ultrasound scan is related to the images. And then they even like try to give us a possible diagnosis, which is a typical small hemangioma. And if you think about this, and if you think that the steps that were done in just a couple of years, this is mind-blowing, in my opinion. Of course, we need to understand if we want to apply these models into healthcare. So we have the huge potential to reshape multiple tasks that we do every day in our clinical practice, as I've just demonstrated with a very with a very small example, we need to understand whether this model can be applied into healthcare, and which are the tasks that they are already ready to be implemented, and those where there is still a lot of risk when this model may be implemented. So according to the current literature, and according also to the current experiment that we are performing in my lab, the main thing that these models are ready to be implemented is related to the assistance in writing medical report and medical summary. They can automate tasks and decrease physician burdens, and they may support for medical coding and administrative tasks. However, if we want to use them for to become like medical assistant, there is still high risk of misinformation and patient harm, and we have a huge risk of leaking patient information. We're going to touch on each of these points in the next slide. So let's start with the point where these models are ready. Why we need something that can ease our medical burden. This is a study performed in 2022, published in 2022, and doctors were asked, how much time do you spend after office hours to write a medical report to finish your administrative task? And most of the doctors spent more than 1 or 2 hours, what we call pajamas work. So when we are at home and we write these notes. And most of the doctors, so 59%, told that they were not in agreement that the time spent is appropriate. So it's a lot of time. And also, they agree that this time spent by writing reports also may reduce the quality of the quality and quantity of time that we spend with our patients. So this is like the foundation on why we may need something that help us in doing some tasks that can be automated. What could we envision with a large language model in such a task? So let's say that we are talking to a patient, and when we talk to a patient, when we are making a diagnosis or when we're collecting the patient history, we check all the relevant information, for example, from labs, from ultrasound, what current medication they're taking, or anthropometric evaluation. So all this information is stored in the electronic health records in our hospital system. So we could see that a large language models has access to this information in the background, and then write a report for us, taking into account all the relevant information from all these different sources. There is only one big study which was published in Nature last year about using LLMs for medical report generation and summarization. What the authors did is that they tested multiple models. So you can see like GPT-3 or GPT 3.5 and 4, or what we call open source model, which are model that are not proprietary from some companies. So you can use them locally. And they tested different techniques for fine tuning, which means giving additional training or using guidelines, for example, to guide the model to give a given task. And they tested four type of notes. So the radiology reports, progress notes, which are notes written during the admission of the patient, or patient health related question, or patient doctor dialogue. So they have to generate summary on these four tasks. And they evaluated for three main quality metrics, which were completeness. So how much is the information complete, how much is correct, and also how much is concise. So the main risk is that if we generate a very long response, it may be too long and we may lose some critical information while reading it. It's not concise enough. As you can see from the results, among the three evaluation metrics, especially for correctness and conciseness, the evaluators didn't prefer neither the human written report or the LLM written report, which means that the evaluation of this task was comparable among the large language models and the human physicians. And regarding completeness, the evaluators preferred, as you can see, GPT-4, so the large language model written report. And this is interesting, in my opinion, and a very valuable result, because we don't need something that outperforms as human, but it should be at least comparable to be implemented. And of course, if it can be better than us, that would be a plus. And when the evaluators also explored for harm, they found out that there was comparable likelihood and extent of harm between language models and human doctors. If you can see here, this is just some of the report brought by the LLMs, and they highlighted in each report, which could be like incorrect thing. And for example, in this report, they found out that one of the hemorrhage in the brain was not located in the left, but the LLM in the left frontal lobe, but the LLM found out right frontal lobe. So as you can see, there still are some critical errors that need to be addressed. I want to talk briefly about the medical coding and possible supporting administrative tasks. So this is important because 4 in 5 medical bills, especially in the United States, have some errors. And these errors may increase the healthcare cost for a patient. And you can see like in a private healthcare system, how this may affect cost and patient satisfaction. So what happened is that we have ICD codes, and these ICD codes are taken from administrative people from the medical notes, and they establish diagnosis and treatment. For each note, so for each patient we have notes, the some administrative people take this concept and then they use them for diagnosis, for example, chest pain, the body part, the symptom, and possible diagnosis. When we used a large language model to extract relevant ICD codes from nodes, so we had the node, and we had also the gold standard ICD code that already extracted, we found out that large language model in 82.7 or 81% of cases extracted correct nodes. And when the authors did a sensitivity analysis between primary and secondary diagnosis of ICD codes, they found out that extraction was less accurate for secondary or tertiary diagnosis when compared to primary diagnosis. So LLMs were able to extract relevant chief complaint in particular. And I want to, so we found something that is, let's say, accurate enough on the 80 to 90% in terms of extracting information. However, what happens if we want to use large language models to give us some medical advice? The huge risk is for misinformation and patient harm. And we've conducted a systematic review related to how accurate are LLM's responses in digestive disease, and we found out that the accuracy range is too broad, ranging from 6 to 91%, and this happened because of three main reasons: the use of foundational models, so they didn't include techniques to include, for example, guidelines. There are still no standardized reporting strategy for results and methodology using LLM in medical studies. And also, when we talk about accuracy or what is accurate or not, there still is no accurate definition of accuracy, and there are no accurate benchmarks to test for accuracy. And this is important because LLMs, or like generative artificial intelligence, should abide of the A3H principle. They should be helpful, honest, and harmless. Because inaccurate information can lead to patient harm. And there are three main strategies that we can use to align LLMs to this 3H principle. And these are the prompt engineering, the retrieval augmented generation, the supervised fine tuning, which we'll be talking about in the next slides. So let's start with the prompt engineering part. A prompt is a series of instructions that we provide to the system in order to guide its way of providing an answer. The standard prompting is just have a question. So Roger has 5 tennis balls, he buys 2 more. Each can has 3 tennis balls. How many tennis balls does Roger have now? This is a very simple answer, as I would ask. There are more complex way of doing prompting. For example, the chain of thought prompting, in which before asking the question, we provide an example. So we provide an example on how we would think to the answer. And this was found to increase output accuracy of 50% compared to standard prompting, which is called zero shot, because we don't provide any example. Another way to increase accuracy is what is defined as retrieval augmented generation, in which there is an external data set, and this data set contains medical information. And each time we ask a new query, there is a search in this external data set, and the model retrieves the relevant information from the external data set and use this external knowledge to provide an answer. So let's say if I'm asking about therapy in general for a patient with chronic hepatitis C, there is a system that search among, for example, I provide the guidelines for HCV, and it will select the most relevant information and then use this information to provide a response. Another technique is called supervised fine tuning. In this case, the information is not outside of the model, so it's not an external data set as in retrieval augmented generation, but is we perform another training, another fine tuning. So we train the model with this external knowledge, and then we integrate this knowledge into the model. So the model, when we ask a new question, it does not retrieve outside of it, but it has this knowledge integrated in itself. However, when we want to inject some knowledge, we need to know if this knowledge is accurate enough or if the LLM can parse this knowledge in a good way. And so we need to be sure that what we're injecting is data of high quality instead of just quantity. And we did a study which was recently published in Nature Digital Medicine with HCV guidelines, and we discovered what we define as the LLM-friendly version of guidelines. So, which is a guideline who does not contain, as you can see here, no text information. So this is an ablation study on the left. What we did is that we added complexity levels in terms of text reformatting. And substantially, what we found is that LLMs cannot parse, for example, flowcharts or tables very accurately. And so we needed to, we created an automated way to convert the guidelines into an LLM-friendly version. So it automatically converted, for example, flowcharts or tables into text. And when we provided this LLM-friendly version, the accuracy in responses were reaching almost 100%. And these results were also validated when we asked the European HCB guideline authors to write us some questions. We proposed these questions to the LLM with integrated guidelines, and then the main authors of the guidelines evaluated the responses. What we found is that using a 10-point scale, these answers were, when we use RAG, so the retrieval augmented generation, responses were deemed as accurate with an average score of 9.1. And if we considered like a binary grading of accuracy, so if the answer is completely accurate or not, we found that the RAG showed an accuracy of 83.3%. So something that is comparable to what we found without employing the main guidelines author. And we also developed a chatbot, which will be released with the paper that is now in a second revision in Libre International. And this chatbot can be downloaded and employed locally. And you can ask like important question of, for example, HIV management in order to access guideline very easily. The problem when we want to deploy LLMs into clinical practice is that we have now several LLMs. So if we don't have only GPT, we have also Claude from Anthropic, we have Gemini from Google, etc., etc., etc. And when we need to evaluate these models, we need to grade them. And of course, grading is a very time-consuming process. So we need to select in some way the best LLMs that is specific to our use case in order to reduce the human labor in LLM evaluation, which is very time consuming. So we need benchmarks. We need a way to define which LLM is the best one. And the European Association for the Study of the Liver, without knowing it, released every 2 weeks some multiple choice questions, which are the campus quizzes. And they are related to multiple topics among the hepatology knowledge. And I just want to show you that, for example, this is a typical question. So it's not that simple question. They're like even more complex question. They provide you like a couple of multiple choice answers to choose. And also they tell you like how many individuals or how many physician takers provided the accurate response. And as another positive thing, they also tell you what is the guideline that the question is referred to, and where in the guidelines is the answer reported. And this is something perfect if you want to benchmark some LLMs, because we have the performance metric of the test takers, but we also know where the information is taken. So we can test retrieval strategies to improve accuracy. And when we tested multiple LLMs with all the guidelines integrated on this benchmark, we found out that, for example, strategies that combine fine-tuning and retrieval produce accurate answers almost 90% of the cases. Another way is to have some tools that do automatic grading for us. And the automatic grading can only be working if you understand what embeddings, so how the transformers works. So as you can see, this is a multidimensional space. And in this multidimensional space, words are represented. So we need to find a way that we can measure the distance between these words in order to automatically automate grading. What happened right now in the field, we use a metric called cosine similarity, and very easily we normalize the vectors of each word into a sphere or another object, and then we calculate the distance among these objects among these words, among these vectors in the sphere surface. And we use this cosine matrix because we calculate the cosine of the angle between the two words according to the center of the sphere. And when the cosine is approximate to 1, it means that the words or the sentence are very close. What we did, we created also an automated way to evaluate answers, and we used word expert on upper gastrointestinal bleeding, so especially like liver-related upper gastrointestinal bleeding, so esophageal varices. And we created a way to compare model answers to expert answers using an embedding model. So we fine-tuned an embedding model, which is how the vectors are created on the expert answers. And we use this embedding model to calculate the metrics of similarity with the experts. And we found that the correlation between this automatic way of grading and the human grading, so of course we graded all the answers ourselves, was 91%. So with a 91% of accuracy, we can automatically grade answers. And this is particularly important because this graph shows 27 model configuration, and this 27 model configuration generated approximately 3,000 answers. So we had to manually grade 3,000 answers. So you would expect that having something automatic may make you not spend all that time in grading, but give you something that you can use automatically and save you a lot of time. The last thing that I want to talk is related to privacy and data security concern, because there are what we call proprietary large language models and local large language models. What happens is that in the proprietary LLMs, every time you have an interaction, every time, for example, you put a message on ChatGPT, this information is leaked with it is leaked to the company. And when you use local model, they are hosted in your, for example, in your laptop or in your local system. So all the information is protected by your local firewall, for example. So there is no risk of leakage of patient information. This is particularly important because we don't want this company to have our patient data. However, there are some partnerships that are happening right now in the US, for example, with Epic, which is the system that is employed in almost every hospital in the US, and OpenAI. So we have local ChatGPTs that we can use, and these local ChatGPTs hosted in the hospital server. So there is no exchange of information between OpenAI, so between the company and between the hospital servers. And I want to give just a few slides on what the future may hold for us, about two things. So ambient AI and AI agents. So ambient AI, we should think of something that, let's say I'm talking to the patient, as I've said a couple of slides before, and this system is listening in real time on what we are saying to the patient, so our conversation, and also has access to all the patient information in the background. And the system can, of course, give real-time warnings if critical information is omitted. For example, I'm talking to a patient about jaundice, and I forget to ask if he's taking any relevant medication that may induce some drug-induced liver disease. So they can give us some real-time warnings on please ask this question to the patient you forgot to ask this question. So it can improve somehow patient safety. They can, of course, produce summaries in real time and create billings, and not only give us warnings, but also give us real-time decision and provide eventual recommendation according to the guidelines and patient record. And I'm saying this because this is already happening in multiple clinics in the US. For example, it's happening here at Yale, it's happening at Mayo Clinic. And there was a study published last year on New England Journal of Medicine using a system of ambient AI, so something LLM that was listening to all the patient-doctor conversation. And of course, they found that it reduced the documentation burden. It improved physician-patient relationship by allowing doctors to focus less time on the screen and increase the number of minutes that each doctor has to talk, to really talk, or banally, more simply, doing a physical examination to the patient. And of course, this enhanced the physician satisfaction and also produced high quality recommendation if it was requested by the doctor. So it was something that wrote the summary for the doctors, gave some real warning. Of course, it was something rudimentary at the moment, but also it could have provided to the doctor some high quality recommendation based on the case. And another thing that is going to happen real soon is the concept of agents. So let's say that our LLM is not accurate enough for a task. So we say that we want to use a system that automates patient treatment for HCV. And if we use a single LLM, it does not work accurately. And so what we do is we divide the task into multiple LLMs. So each LLM has a given task. So let's say I want to treat a patient with HCV. I have one LLM that check the genotype and provide recommendation based on the genotype. Another check therapy history and provide recommendation accordingly. Another the fibrosis status. Another the current therapy, and another, for example, current prescription that the patient is taking. And when you have like multiple LLMs, each with a given task, and they're talking to each other, we performed a study which was recently published in Hepatology. When we use local LLMs, which are less powerful than proprietary LLMs, the accuracy jumped from 24% when we had only one large language model that took care of all the tasks to 89%. So when we split the task into multiple LLMs doing different jobs, they can drastically increase performance and accuracy. And if you think about this, you can have like a virtual liver clinic where you have an LLM or a group of LLM which are taking care of the patient prescription refilled or even like prescription of the first therapy. And the last thing that I want to say to all of you is that given that a lot of clinics, especially in the US, are already integrating the system into their local hospital settings, there are people within the hospital boards that are saying, who is the ability of this generative AI system? And let's say I'm prescribing to my patient video capsule enteroscopy to check for some vascular malformation, and the Gen AI system misses the vascular malformation, so the patient bleeds and die. In this case, who is liable of the mistake? So if we think as AI as a second observer, so the AI is just telling us, it's giving us some suggestion, but the first decision is still to the clinician. So there is actually no change in our workflow because we are just using AI to support our decision, but we are still reviewing all the charts, all the images, and we are making the decision. It's not the AI making the decision for us. If the AI is the one who provides the recommendation without human supervision, of course, the fault is of the AI system. And in case of the AI system produce a wrong misinformation, is fault of the hospital or the fault is of the company who developed the AI system? So there are still a lot of discussions happening in hospital boards regarding possible lawsuits from malpractice generated from generative AI, and we think that most of our government, especially in the US, because the EU is still a little bit behind on this, will probably block at some point implementation without some clear regulation. And we'll see what's going to happen. But this is happening already. So we need to be ready about generative AI being implemented in our everyday workflow very soon, especially here in the US, as I've said a couple of times. And to conclude our talk today, I know that I gave you a lot of information, but we need to have the basic to understand this complex couple of systems. I want to like give you like some take-home messages. First of all, is I think that we think that generative AI is the first technology that really holds the potential of reshaping medicine, because it can work at every step in our clinical support, clinical decision, patient management, or more administrative tasks. And Gen AI is already comparable to humans, physician in task focused on summarization and extraction of concepts. However, we need to be aware of two main risks. The risk of harming patients, because LLMs in general, and in general, generative AI are not accurate enough yet to produce accurate information all the time, especially without more refined strategies to include domain knowledge, as I've shown you before, like retrieval, augmented generation, or fine tuning. And we also need to be very aware of potential data leakage with proprietary models. So if you ever think of writing something on ChatGPT with patient data, don't do that, because you will be leaking your patient information to the company. And that's it. Thank you all for listening to this talk. And you can find my email if you ever want to contact me for collaborations or just to ask more questions about this topic. Thank you.
Well, thank you very much, Mauro. It was an excellent presentation.